Hello everyone and welcome to a live stream of Chemistry 223. This is for the summer term. My name is Travis. I'm a chemistry tutor at the Portland State Learning Center. I hope you all are having a fun time with chemistry so far this summer. Today we're going to get started with chapter 14, talking about acid-base reactions, acid buffers, and titrations of acids. So first I wanted to post a few links. We have a link to the Learning Center's webpage as well as their Facebook and Instagram. Check out the webpage, follow them on Facebook and Instagram for updates of new things, new exciting resources they're having available. You can also get links there to Penji, which is how we schedule our online tutorings for the summer. You can schedule a tutoring session with our chemistry tutor, Amir. And you can also check out my chemistry drop-in tutor sessions, which is after the Saturday live streams up until 5 p.m. I could also give you a link to the Portland State's YouTube channel. This is actually a playlist where all of these videos that I make are posted up on there. So if you ever want to go back and look at one of the past videos for Chem 223, you'll find them on that playlist. If you search around, there's also playlists for Chem 221 and 222 that I've done over this last summer, so you can stay updated and kind of go back and check out what you learned previously. I know you guys go through this really quickly and there's a lot to learn. So let's get started. We have about 14 problems or so to go through today, so I'm going to jump right into it. Switch over here. This first problem here is really just identifying and labeling the Bronsted-Lowry acid and its conjugate base, as well as the Bronsted-Lowry base and its conjugate acid. So for each acid, there's a conjugate base, and for each base, there's a conjugate acid. Yes, this chat works. The chat does work for asking questions. Feel free to ask any questions you'd like, and I'll do my best to cover them as well. Thank you for chiming in. So in this problem here, we're going to identify which one of these are acids and which one are bases, and what are the conjugate acids and bases for each of those equations. For part A, you should know I like to reference an acid kind of like this is HA. It's some compound with a hydrogen that it can lose, because acids are a hydrogen donator. They donate protons to bases, and bases I will often refer to as an A minus. So it's lost that this whatever compound A it is has lost its hydrogen and now has a slightly more negative charge because of that. So when we're looking at these acid and base compares, we can see that if you compare the reactants to the products, you should see that it's either gained or lost a hydrogen in that process. So looking at this first one for part A, we have NO2 minus. So NO2 minus is, and we compare that to our HNO2, which is just a neutral atom, a neutral molecule. So the base is going to be that NO2 minus, because it's missing that hydrogen and it's gained that hydrogen, so it's a conjugate acid on the right hand side, the product side of things. If we look at H2O in this case, since it's reacting with a base, it's acting as an acid, and therefore its conjugate base is always going to be the hydroxide there, the OH minus. For part B, we're looking at HBr and HO2. So HBr is one of our strong acids. So is HNO2, that's nitrous acid. So HBr is hydrogen bromide. And that's going to be one of our strong acids. It fully dissociates, and so that's definitely going to be an acid on that side here, which means that water is going to act as a base. In this case, you see that water can act as both an acid or a base, gaining an electron, becoming hydronium, which is this H3O+, or it loses an electron and becomes hydroxide, which is what happened on part A. So that means that hydronium is going to be the conjugate acid to the water base, and then that bromide is going to be the conjugate base of that HBr. Part C, we have a HS minus plus H2O is produces H2S plus OH. So anytime we see this OH over here, we know that's going to be our conjugate base on the product side, meaning that H2O is acting as an acid. And we can see that HS is gaining a hydrogen, so it's acting as a base on that hydrogen, gaining that proton on there. So we can say that is going to be a base. Go back to my base and conjugate base, or conjugate acid for H2S in that regard. For part D, we see H2PO4 minus plus OH minus is producing HPO4 2 minus plus H2O. So in this case, we have this OH minus, this hydroxide, which is acting as a base, and it's producing water on the right hand side, so that would be its conjugate acid. And that H2PO4, although it has 2 hydrogens to lose, it loses one of those to create that HPO4 on the right. So this would be an acid, and this would be a conjugate acid. For part E, we have that H2PO4 minus again, plus HCl. So HCl is one of your strong acids in this case. So notice it's producing H3PO4. So the H2PO4 can act as an acid or a base, because in this case it's gaining a hydrogen, it's gaining that proton. And HCl is a stronger acid, so it's going to be acting as an acid. And that means that the conjugate base for HCl is that same thing minus that hydrogen. So H3, so HPO4 is still a conjugate acid, for which HPO4 is, oh, you're right, that should be a conjugate base. I'm sorry. Yeah, because it should be a conjugate base because the acid has a conjugate base. Yeah, thanks for clearing that up. If you spot anything that I'm doing wrong, definitely point it out to me, or if it doesn't make sense, I'm happy to go back and look at it, because I do make mistakes at times. Anyways, for part E, H2PO4 is a base, and it's going to be creating that conjugate acid, H3PO4, because it's now gaining that proton from that HCl. So that's a quick way to kind of go through and look at what's an acid and what's a base when you can see the entire equation, because you can see what's gaining a hydrogen, what's losing a hydrogen. And if you ever have water in there and hydronium or hydroxide, hydronium is always going to be an acid, hydroxide is always a base, and water can act as either. I'm going to jump on to part 4, or number 14 here. So this says the self-ionization of water is the self-ionization of water endothermic or exothermic. The ionization constant for water at 40 degrees Celsius is 2.9 times 10 to the negative 14th power. And at 60 degrees Celsius, it's 9.3 times 10 to the negative 14th power. So how I would tackle this problem is, first I was write the kind of reaction equation, the balanced chemical equation, where it's H2O is in equilibrium. That's going to be a liquid with H3O plus aqueous plus OH minus aqueous. So that's the standard acid-base water self-ionization reaction. And we can see that Kw is going to be equal to the concentration of hydroxide times the concentration, or sorry, of hydronium times the concentration of hydroxide. And they're saying that this is going to be equal to 2.9 times 10 to the negative 14th power at 40 degrees Celsius, and equal to 9.3 times 10 to the negative 14th power at 60 degrees Celsius. So we can see that they're increasing the temperature, and we're seeing a change in that Kw. So what that means is we have to see what does that change in temperature mean versus whether it's endothermic or exothermic. And when we went over in Chem 222 is if it's endothermic, the way I see it is heat is a reactant. Because if it's endothermic, that means it's absorbing energy from its surrounding areas, and it's the energy level of the product is going to be higher than the energy level of the reactant. If it's exothermic, heat is a product. So the way I would test this to see, well, what happens when we heat up, where between these two, we're increasing the temperature from 40 degrees to 60 degrees, and we can compare those kW values. And you can see which one's higher. In this case, the 60-degree one is going to be higher than the 40-degree one, which means that as you add heat to it, the kW value is increasing. The only way for that to happen is if your concentration of hydroxide or hydronium is increasing, probably both, right? So those concentrations are going up when that happens. If the concentrations are increasing on this side, there's something driving this equilibrium to the right-hand side. It's shifting the equilibrium towards the right. And if that happens when you increase that heat, that means that heat must be a reactant. So if the heat's the reactant, because that's what's increasing, driving Le Chatelier's principle says we then increase one of the reactants, we're driving the reaction towards the right-hand side. That drives the kW value to be a larger number, and we get an endothermic reaction, not an exothermic. So that's kind of the way I look at that type of problem. Go on now. Again, if you have any questions, feel free to chime in. This next one, number 18, says calculate the pH and the pOH of each of the following solutions at 25 degrees Celsius, for which the substance is ionized completely. So they have a few concentrations here: HCl, NaOH, HNO3, and Ca, or say calcium hydroxide. And one thing I like to point out here at this point is this nice pH cube or square. So this has a relationship between the concentration of hydrogen ions and the pH, as well as the relationship between the pH and the pOH, and the relationship between the pOH and the OH minus, the hydroxide concentration, as well as the hydroxide concentration and the hydrogen ion concentration. And it all comes down to a few different calculations and expressions. So up here we can see that if you take the concentration of hydrogen ions, multiply it by the concentration of hydroxide ions, you always get this 10 to the negative 14. And that's at standard room temperature, 25 degrees Celsius. So we can use that relationship to calculate one from the other. We can also call this the standard kW, which is that equilibrium constant of those two. So we can say if we had the hydroxide, we can then calculate back to the concentration of hydrogen ions. We can also use this equation here to go from hydrogen ion concentration to pH. Going the opposite way, use this one to go from hydrogen ion to pH, and then use the other one to go from pH to hydrogen ion concentration. And you can work your way all around that cube to get all of those 4 different values just with those few different equations. It's a really useful thing to have handy, written in your notes and stuff like that. So I always plop it on the problems when I start to use them. So in this case, we want to calculate the pH and the pOH of these different concentrations. And using this equation here that says the pH is equal to the negative log of H plus, we can see in this one, when they add that HCl, it's fully disassociating. We can say that the concentration of H plus is equal to the concentration of HCl. So in this case, that's going to be equal to negative log of 0.200, which, if I plug into my trusty calculator, Well, I hit negative log of 0.2. That's equal to 0.6. How many sig figs are we doing? 399. And that makes sense because we're adding a strong acid to water. So that strong acid is going to fully dissociate. There's not really going to be anything that's really basic in there. And we get a very, very acidic solution. It's going to be acidic. And that's for the pH. If we want the pOH, notice we can just say the sum of the pH and the pOH is equal to 14. So we can say that's going to equal to 14 minus the pH, which is equal to 14 minus 0.699. So 14 minus this value, we can see is equal to 13.30, or 3, keeping 3 sig figs. Actually, I should go one more. Boom, boom. There. That makes me happier. So that's the pH and the pOH of part A. We can do the same thing for part B, saying the pH is equal to negative log of, in this case, they're giving us sodium hydroxide, actually. So I should use that to calculate the pOH, because that concentration of sodium hydroxide is going to be equal to the concentration of hydroxide, because it has that one-to-one dissociation. So I can put in here now 0.0143, and I can find the pOH of that. So negative log 0.0143, and I'll put a decimal place in there. There we go. So I can see the pOH is equal to 1.84. To get the pH, that would equal 14 minus 1.84, which is equal to 12.1 or 12.2. And that's going to be very basic, because it's a greater pH than 7. And we can see we're adding a base to water, so it should be very basic. Here, that part A, we added an acid to water, so it should be very acidic as well. Part C, this is another one of our very strong acids. It's going to fully dissociate into it. And we can see it has a 3 molar concentration. So our pH is going to equal negative log of 3.0. Now when I do negative log of 3.0, I get a negative number. This is going to equal negative 0.48. And that seems weird, but it's really correct. It's so acidic because we're adding a strong acid to it, a high concentration strong acid to water. It makes it so it's so acidic that it's a negative pH on that scale. If we were to find the pOH based on that, would be equal to 14 minus that negative 0.48. 14 minus that value is going to be equal to 14.5. And you can see that pOH is actually greater than 14 as well, which is understandable. So that's the pH and the pOH for that one. For part D, we have calcium hydroxide there. Notice that it's a CaOH2, so there's 2 hydroxides for every 1 calcium atom that's on there. So when we figure out the concentration of hydroxide, we have to take the concentration of calcium hydroxide and double it. Because for every calcium hydroxide mole, or for every mole of calcium hydroxide, there's 2 moles of hydroxide in there. And what we want is that concentration of hydroxide. So if I find the find the pOH. That's going to equal negative log. I'm going to write it as 2 times 0.0031. Because that's what we're doing. We're doubling that concentration in there. So that's negative log of 2 times 0.0031. And that gives us a pOH equal to 2.21. Let's say 2.2 for 2 sig figs. The the pH would be equal to 14 minus 2.2, which is equal to 14 minus 2.2. I hate rounding errors, so I always grab the last number from my calculator, and that's 11.8. Or just say a pH of 12 if we're sticking to that and here it's say 11.8. For sig figs, when you're subtracting, you do the last common decimal place, and I'm going to say that 14.0 is a standard conversion rate, so I wouldn't round my sig figs to that. So that would be my answer to part D. The pH is at 11.7. This is going to be very basic, which makes sense. We're adding a base to water. For part C, we're adding an acid to water, and we can see the pH is incredibly acidic. So that makes sense. I always go back and try to think, do my answers make sense based on what I know about the chemistry that's happening. So for part number 36 here, they say, what is the ionization constant at 25 degrees Celsius for the weak acid CH3 2 NH2? So that's going to be dimethylamine. So there's 2 methyl groups attached to an amine, and the conjugate acid of the weak base CH3 2 NH. So that's that dimethylamine where it lost one of its hydrogens. And it gives us this Kb value there. So the constant of the base is 5.9 times 10 to the 4th. So the reaction that's happening here, I'm going to write it here, CH3 2 NH2 plus aqueous plus H2O liquid is producing CH3. There's 2 of those, NH aqueous plus hydronium. So we can use that equation to write down what the expression for the Ka value would be. The Ka would equal its products divided by its reactants. So in this case, that's the concentration of CH3 2 NH. I'll leave the aqueous off, times the concentration of hydronium divided by this concentration of CH3 2 NH2 plus. So that's just the reactant there goes on the bottom, and the products there go up on the top. And that's going to be our Ka value. We can do the same idea with the Kb. I'm going to rewrite this equation. I like to do this just so we can really see how it all comes together. I'm going to rewrite it backwards because it's really an equilibrium. It's going back and forth. Plus, in this case, it's still water to produce the CH3 2 NH2 plus aqueous plus OH. So that compound is reacting both with the water to make a hydronium and hydroxide. They're going back and forth depending on whether it's the conjugate base or the acid going through. So here we can write our Kb value which is then going to be equal to that concentration of CH3 2 NH2 plus times the concentration of OH minus divided by that concentration of hydronium. Oh, I'm sorry, of CH3 2NH. And notice I have hydroxide on the top when I'm doing my Kb value, and I have hydronium on the top when I'm doing my Ka value. And the nature of these two is, we can say that Kw is equal to Ka times Kb. So we can convert back and forth between those using these reactions, and we can see that if we multiply these together. So if I do that Ka, I'm going to do a quick copy and paste so I don't have to write that all over again. Is there. I'm going to multiply that by Kb. Is there. And see if I can move it over because I ran out of space for it all. Good enough. And we can see when I multiply these two together, we get a few things that cancel, leaving us just the hydronium concentration times the hydroxide, which is the definition of Kw. So to find out what this ionization constant is for the weak acid, we're really looking for that Ka value, and we can find that by taking Kw divided by Kb. Kw is always 10 to the negative 14th power, at least at 25 degrees C, and Kb value they give us here. That's 5.9 times 10 to the negative 4th. So I'm going to write 1 e to the negative 14 divided by 5.9 times 10 to the negative 4th. That's going to equal 1.69, I say 1.7 times 10 to the negative 11. That's going to be our Ka value. And then the question is, does that make sense? We have a weak base, which has a Kb value of 5.9 times 10 to the negative 4th. It's going to have, it's a weak base, but it's not like a really, really weak base. So its acid, or the Ka value, is going to be even weaker than that. It's going to have a weaker acid than it is a base because that exponent is to the negative 4. If that was closer to negative 9, then it would end up having a Ka value that's larger than. And that threshold that tips it back and forth is kind of around negative 7, because that's what gives you that kind of that pH value of 7. It's close to water at that point. So next one. Here they're asking basically which one of these is the stronger base and which one of these is the stronger acid. And we can use that by determining our Ka values and Kb values for those. So the easy way to do this is look them up in tables. So I happen to go into the textbook. In the back, there's Appendix I, which has ionization constants of weak acids and bases. Switch over here. There we are. And we have dimethylamine and methylamine. These are what they look like here, where it's one methyl group attached to that NH, or two methyl groups for the top one methyl group for the bottom one. And they give us the values there of 5.9 times 10 to the negative 4th. That's one we just used. And 4.4 times 10 to the 4th. And these are all Kb values here. So switching back, that's telling me that this value is 4.4 times 10 to the negative 4th for the Kb. And this guy is Kb equals 5.9 times 10 to the negative fourth. And we want to know which one's the stronger base. Well, just as we said before, go back to my definition of my Kb, the stronger base, Kb is down here, the stronger base is going to have produce more hydroxide in the reaction, right? So the stronger base is going to have the larger Ka value, or sorry, Kb value. So in this case, this value here is going to be larger than the other, so that's going to be a stronger base. To find the Ka values of these conjugate acids, we can say that that's going to equal Kw divided by Kb. Oops. So doing that for each of those, I'm going to take this one down here and say 10 to the negative 14th power divided by, well, the conjugate base for this guy is this one. Nope. It's this one here. So that's going to be 5.9 times 10 to the negative fourth, which is equal to 1.7 times 10 to the negative 11. I just calculated that last question, didn't I? I'll do the same thing here and take that 10 to the power of negative 14 and divide by, we said 4.4 to the negative 4. That's going to be a Ka equal to 2.27 times 10 to the negative 11. So comparing these two values, this guy is a stronger acid. It's still a very weak acid, but it's stronger than the other one we're comparing it to. So notice that the stronger base has a weaker acid, and the weaker base has a stronger acid. And that relationship is going to go back and forth between those. Anytime you have a really strong acid, it's going to have a really weak base to it. The base is essentially really stable, and it doesn't like to take on another hydrogen. And the opposite's also true. So let's look at this one. This one's a bit more conceptual, but I like it because it has to deal with the Le Chatelier's principle and how adding either a base or an acid is going to change and shift the reaction one way or the other. So for this first one, first of all, for which of the following will increase the percent of NH3 that is converted to ammonium ion in water? So ammonium is NH4 plus. So really what we have is this reaction here. This NH3 aqueous plus H2O liquid is in equilibrium with NH4 plus aqueous plus OH minus aqueous. So that's the basic reaction for what's going on. This equilibrium between hydronium and ammonia, or ammonia and ammonium. So when we add NaOH, we're essentially adding to that some OH minus. We're increasing the concentration of OH minus in that equilibrium. And Le Chatelier's principle says if we increase the product, it's going to drive the reaction, or shift it back towards the reactant side. So by increasing the OH minus concentration, that hydroxide concentration, we're going to reduce the production of NH4 that's in there and driving it to less. So that's going to decrease the NH3 to NH4 plus production. For part B, we take that same equation, but now we're adding HCl. So what happens when we add HCl? So I can rewrite the HCl acid-base dissociation plus H2O liquid is in equilibrium with H3O plus aqueous plus chloride. Chloride is a really weak base. Basically, it's incredibly electronegative. It has a big atomic size, so it distributes that negative charge over its full outer shell. So it's not really looking to pick up another hydrogen pretty well. So it basically just disassociates and then floats as an ion in water, which is why HCl is one of the strong acids. In this case, we can see what we're doing essentially is adding hydronium to that equation, because chloride's not going to react with anything, but that hydronium is going to do something. Because that hydronium, when I add hydronium now, that's going to react with the hydroxide to produce H2O liquid. So when that happens, we're essentially reducing the amount of hydroxide now. Okay. Going back up to my original equation, we would be reducing this concentration of hydroxide in that equilibrium, which would then drive this reaction to happen more often. And I know I'm writing it up on A. I should really do a copy and paste to my original copy. There we go. So by reducing my hydroxide, I'm driving the reaction more to the right, causing more of that product to be created, which increases the NH3 to NH4 plus production. The last one on this one is part C, which is NH4Cl. So you might guess, just by looking at this, NH4Cl is going to disassociate. Chloride is going to be floating around in water, just happily floating as an ion. And NH4 is going to be floating as a positively charged ion. And essentially, we're going to increase that NH4 concentration. And by doing that, very similar to part A, we're going to shift to this equilibrium towards the left-hand side. So I'm simply just going to say shifts left and decreases that production. So anytime we're shifting left, this reaction happens less. Less of the ammonia becomes ammonium. There we go. And that's it for this problem. Let's move on to 53. So for 53, we are going to utilize that Ka, Kb equation, where I'm going to say my the concentration of the base times my hydronium concentration divided by the concentration of the acid. That's going to be my Ka equation. My Kb is equal to the concentration of my acid times OH minus hydroxide divided by the concentration of my base. So just looking at these, we can tell kind of which one's the acid and which one's the base and which one's hydronium. It tells us kind of what we're starting with there. So we can compare that, say, to this one and see that the second one here is missing a hydrogen. So it's got to be our base. So for part A, we can then just plug in. First of all, we know this is our acid, so we're going to have a Ka value. And that's going to equal the concentration of our base, which in this case is 1.34 times 10 to the negative 3, times the concentration of hydronium. Notice it's the same value, 1.34 times 10 to the negative 3. And that's because every conjugate base that's created from our acid, it's because it's lost that hydrogen and created a hydronium ion. So those are almost always, if not always, going to be the same value. And we're going to divide then by the concentration of our acid, which is down here at 9.866 times 10 to the negative 2. So now it's plugging that into our calculator. So a lot of these acid base, it's knowing kind of how the reactions are happening, figuring out the variables you need and plugging them into these equations. But you have to kind of know how to work your way around the equations because they can be a little cyclical, so you can try to figure out how to manipulate one to get to the other one. So in this case, I have 1.34 times 10 to the negative 3. I'm going to go ahead and square that because I'm multiplying it by itself and then dividing by 9.866 times 10 to the negative 2. That's going to equal 1.82 times 10 to the negative 5. And that's going to be my Ka value for part A. For part B, I'll switch colors and I can alternate. For part B now, I'll draw a line there. We're starting off with this ClO minus. So that's going to be a base. See if I can make that a little bit bigger first. The ClO minus is a base. And you can notice we have that concentration of hydroxide there. So we're going to have a Kb value. And that Kb value is going to be equal then to the concentration of our acid, which is the same base. That's the conjugate acid of that base. Now it's going to be 2.38 times 10 to the negative 4. And we're going to multiply that times the concentration of our hydroxide, 4.0 times 10 to the negative 4. We're going to divide the whole thing by the concentration of our base, which was there, 0.273. We can plug that in and see what we get. So that's 2.38 times 10 to the negative 4. We're going to multiply that by 4.0 times 10 to the negative 4. And divide that by 0.273. And notice the two factors on the top on the numerator are not the same for the base Kb reactions. And that's going to be very common. So we can see that this is 3.49 times 10 to the negative 7. And that's going to be our, I should change that to 3.5 for sig fig values. This value is 2 sig figs. Because of that, we have to round to that 2 sig figs. But 3.5 times 10 to the negative 7 would be our Kb value. For part C, let's box this in. Part C, we're looking there. We can see we have this and we have hydronium. So that's going to be an acid. So we're going to have a Ka value. That Ka is going to equal then the concentration of its base. Make that a little bit bigger. So we have the concentration of the base times the concentration of hydronium divided by the concentration of the acid. So the concentration of the base is 9.8 times 10 to the negative 3. Concentration of the acid is the same. Gonna go ahead and just put a little square there. And we're going to divide that by its concentration of the acid, which was, there it is, 0.524. So it's 9.8 times 10 to the negative 3. I'm going to go ahead and put up little brackets around that. Should have put that parenthesis in at the beginning. So I can square it, divide it by 0.524. That's 1.8 times 10 to the negative 4. So that's going to be our Ka value for part C. Part D, it's the same idea. Here we have hydronium, so we know we have a Ka value. And that's going to equal then 2.3 times 10 to the negative 3, the concentration of our base, times that hydronium, which should be the same. So square it, divide by the concentration of our acid, which was 0.233. Remember my parenthesis this time. The negative 3. Oh, I got trigonometry in there. I can't do that. All right, square that, divide by 0.233. And that gives me 2.27 times 10 to the negative 5. 2.27 times 10 to the negative 5. That's going to be my Ka values. So for all of these, if I wanted to find the Kb values or the Ka values, the other constant, I can just take Kw and divide by Ka to equal Kb, or Kw divided by Kb to equal Ka, if you ever want to find one from the other. Next one we're going to do is number 66. Here the pH of 0.15 molar solution of HSO4 minus is 1.43. We want to determine the Ka for this HSO4 minus from this data. So here we actually need to find out what that Ka is from knowing the concentration and the pH. And we can do this using that Ka equation, but we need to make sure that we have the concentrations when they're at equilibrium, not the initial concentrations of the solution. Because if you put this into water, some of it's going to break down and create its conjugate acid or conjugate base. In this case, we're looking at a conjugate acids, or we're looking at a conjugate base because this is an acid. It's a fairly weak acid, but it's still an acid. What is it? Yeah, it's definitely an acid. It could be both. It's ambiprotic. So to start out with this, I would start out by writing out a rice table. And we went over this on Saturday for Chem 222. If you missed that video and you're confused about what rice tables are about, definitely go back and look at my Chem 222 playlist and find the video where I talk about rice tables. It's probably towards the end of that video. And I'm going to go over it here, but I'll kind of run through it. So the rice is reaction, initial, change, and equilibrium. So what we want to do is write the reaction down to begin with. So that's HSO4 minus aqueous plus H2O liquid is going to be in equilibrium with SO4 minus aqueous plus hydronium. And then we want to write the initial concentrations for everything. So for liquid, we don't care about liquid. The water, it's our solvent. So we kind of leave that out of the concentrations. But we know our initial concentration of HSO4 minus is going to be 0.15 molar. We know our initial concentration of SO4 minus, that's 0. And the initial concentration of hydronium is technically 10 to the negative 7. But it's essentially 0 in this case. And we can look through the math of it, and you'll see that it basically gets lost in sig figs. But I'm going to say that's essentially 0. Makes our life a little easier. So then we look at the change. The change that's happening here is, excuse me, some of those hydrogens on the HSO4 are leaving the SO4 and bonding onto the water molecules to create hydronium. So we're having some of this concentration is going to go down, some number of moles of that. And at the same time, we're increasing the concentration of SO4 by a 1-to-1 ratio, as well as increasing our hydronium by a 1-to-1 ratio. So we can write at equilibrium, basically, the sum of these. I'm going to draw a line here, just adding up the two values above it in the column. That's 0.15 minus x. For SO4, that's just going to be x, and for hydronium, it would also be x. And this is where you would lose the 10 to the negative 7. So if this was 10 to the negative 7 plus x, as long as x is greater than 10 to the negative 5 or so, or even negative 6, depending on your sig figs, you're going to lose that 10 to the negative 7 completely once you make that addition, which is why we say it's essentially 0. So in that case, hydronium concentrations are just going to be x as well. So now we can plug this into our Ka equation. Well, Ka is going to be equal to the concentration of the base. So that's going to be x. Just say x times the concentration of hydronium, which is also x, divided by 0.15 minus x. Now, one thing that they do tell us here is they're telling us the pH of the solution at equilibrium. So that's really useful because we can use that to determine what the concentration of hydronium is to essentially solve for x in this case. So how we can do that is we know that the pH is equal to the negative log of the concentration of the hydrogen ions, or hydronium. So we can then multiply each side by -1. So we have the negative pH is equal to the log of hydronium, or hydrogen ions. And then we can take each side, say 10 to the power of that side. So I say 10 to the power of negative pH is equal to 10 to the power of log of hydronium. We basically get the 10 to the negative pH is equal to the concentration of hydronium, or hydrogen ions. So knowing the pH there, we can plug that in. And that's 10 to the negative 1.43 is equal to our H plus concentration. Doing that real quick, put my calculator on that side this time. We have 10 to the power of negative 1.43. And that's going to be equal to 3.7 times 10 to the negative 2. That's the concentration of H plus. So we can now plug those in for x, because this is really equal to x. H plus is really equal to the concentration of H3O plus. They're the same idea. Hydronium and hydrogen ions. Anytime you have a hydrogen ion floating in there, it's going to bond to water, create hydronium. So I use them interchangeably. So now substituting those values in for here, for x, I'm going to just write this as 0.037 squared divided by 0.15 minus 0.037. And then plugging that into our calculator, this guy here, we're going to square that value. So I'm actually going to put parentheses around it. I don't trust it when I have an exponential like that. Squared. Divide by parentheses for the whole denominator, 0.15 minus this value. And that gives me a Ka equal to 1.2 times 10 to the negative 2. And that's how we can solve that Ka. Just setting up that rice table so we know what those are, and then plugging in and solving for x using the pH that we were given. Finding the concentration of hydronium and saying that that's equal to x, which is equal to the concentration of SO4 minus, and then subtracting that concentration from our initial acid concentration. The next problem, number 81. And I've got a few more to do. I'm going to keep working on these just because I want to make sure we cover all this material. There's a lot to cover today, like I said. So for 81, what is the hydronium solution or hydronium concentration in a solution of 0.075 molar HNO2 and 0.03030 molar NaNO2? So here they're giving us two different compounds and two different concentrations, and they want to know what is the hydronium concentration. So again, I would make a rice table. And we can run through that. That's going to be HNO2 plus H2O. This is a liquid. This is aqueous. Is in equilibrium with H3O plus aqueous plus NO2 minus aqueous. There we go. So the initial concentrations that were given here, they give us 0.075 molar of the HNO2. Water is, again, we don't really consider water. It's a it doesn't have a concentration in itself. Hydronium starts off at 0, or approximately 0. Like we said, 10 to the negative 7 is pretty much 0. And NO2 concentration is going to be 0.030. Now the change in that concentration, again, this is going to go down by some value x number of moles. At the same time, we're going to go up by x here, and we're going to go up by x there. That means that at equilibrium, we're going to have 0.075 minus x for my HNO2. We're going to have x for my hydronium. We're going to have x for my NO2. Or not just x, I'm sorry. 0.030 plus x. There. And they tell us our Ka value already. We need to find that concentration of hydronium at that point. What is x essentially? So we can say that Ka is equal to that 4.5 times 10 to the negative 5, which is equal to, and I'm just going to plug in these values now. It's the concentration of NO2 minus, so that's going to be 0.030 plus x. And we're going to multiply that by the concentration of hydronium, which is just x, divided by 0.075 minus x. So it's the concentration of our reactants divided by our concentration of our products. That's always going to be your equilibrium constants. And now we just have to solve for x. We end up with this crazy little quadratic equation. And we're going to do a little bit of math here. I know math is fun for everyone. I enjoy it. So to do that, I'm going to multiply first by the denominator on both sides. And that cancels this out, simplifying the equation a little bit so you don't have fractions. So now I can distribute this 4.5 times 10 to the negative 5 into each of those values. So this times x, or negative x, and this times the 0.075. So just writing that out, first I guess I should do that math. That's 0.075 times 4.5 e to the negative 5. So that's going to equal 3.375 times 10 to the negative 6 minus 4.5 times 10 to the negative 5x. Scoot that down a little bit. Ooh, should have had a lasso. There we are. And that's going to equal now this, again, distributing this x into each of these as well. That's 0.030x plus x squared. So now we're going to combine Arlow-like terms and move everything to one side of the equation. So to do that, I have to add this x term to both sides, and I have to subtract this constant term from both sides. When I add this x term to this x term, we can see this is 4.5 times 10 to the negative 5. This is basically 3.0 times 10 to the negative 2. Since we sig fig says the last common decimal place is where we'd round to, this term completely gets left out in there. And you could do the math on there, and you can then round to the last common decimal place, and you'll see right away that this term doesn't matter here, this part. So it's gonna get lost in sig fig. So we can put it in our calculator. 0.02 or 3 minus 4.5 e to the negative 5. And we can see that it's 2.9955 times 10 to the negative 2. Rounding to 2 sig figs brings us to, or the last common sig fig would be the third decimal place there, which would still be 0.030. So this is going to end up being 0 is equal to the x squared plus 0.030x minus 3.375 times 10 to the negative 6. So now we have our quadratic equation. And here we actually have to solve our quadratic equation. And to do that, we use the quadratic the quadratic equation. So that's x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And that's because we have it in the form of ax squared plus bx plus c, where a is equal to 1, b is equal to 0.030, and c is equal to a negative 3.375 times 10 to the negative 6. So it's really just a big expression now we have to plug in. So that b is negative 0.030 plus or minus the square root of, and I'll continue that, 0.030 squared minus 4 times 1 times negative 3.375 times 10 to the negative 6. We're going to divide that whole thing by 2. Now notice that plus or minus is still in there at the moment because that's the standard quadratic equation formula that we would use. In this case, since this value is negative, and we are talking about real tangible concentrations of what this x should be representing, we don't want to come back with a negative value. So not only does this have to be positive, but this second term over here must be greater than this first term. Otherwise, we end up with that positive number. So I'm going to take off the minus, and then we can just calculate all of this as 1. So plugging this into the calculator, I'm going to have negative b. I calculated that b. I'm going to use that so I don't have a big rounding error, even though it does kind of get lost in sig figs. Negative b plus the square root of, I'll put parentheses, put my b value in there, squared minus 4 times 1, which is just going to be the same. I'll leave that out. So times, put parentheses, a negative 3.375 times 10 to the 6. So by having them all saved in my calculator, I can just go back and select them really easily. I like that. And at the end, I think I have to put a parenthesis at the beginning. What did I do? To make sure I am dividing everything by 2. There we are. So x is equal to 1.12 times 10 to the negative 4. It's really just plugging in those values and getting the right thing. So this is going to be equal then to, looking back at our table, the concentration of hydronium, which is what they were asking us for. We could use that then if we wanted to. If they were asking to find the concentrations of HNO2 as well as NO2 minus, we can figure those all out just by doing the math for those and plugging x into those. They weren't asking for it, so I'm not going to go through and do it. But now that we have that, we can solve for everything. Number 87. Now we're getting into the idea of buffers. Buffers are when you have a weak acid or a weak base, and you've usually you would titrate in a little bit of the strong acid or strong base, depending on which one you were working with. Sometimes you'd also just mix an acid and its conjugate base together, so you get this buffer solution. So the pH stays right around that level a lot more when you're doing different reactions and stuff. To utilize these, here we want to calculate the pH of this buffer solution prepared from 0.155 mole of phosphoric acid and 0.25 mole of KH2PO4 and enough water to make 0.5 liters of solution. So to calculate these buffers, we use the Henderson-Hasselbalch. Hasselbalch. I spelled that wrong. ALCH equation. And that states that the pH is equal to the pKa plus log of the concentration of the base. So I'll actually put A minus divided by the concentration of the acid. And those concentrations are, of course, moles per volume. And since they're all mixed into the same solution at the end of the day, we want to make sure that the total volume for both of those are the same. So that essentially cancels those volumes out. And it gets me to how I like to look at this, which is the moles of base divided by the moles of acid. Because that's really what matters in this buffer solution. It doesn't matter about the volume as much as it matters that mole-to-mole ratio of base versus acid. And that's going to help us determine what that pK is, or what that pH is. I should mention we haven't talked about pK. I assume you've learned about it. It's the same idea as pH, but now the pK is going to equal the negative log of the Ka. You might say the pKb, which is equal to the negative log of, I shouldn't put those brackets, those imply a concentration, just Kb. So whatever that Kb value or Ka value is, you can use to determine the pKa and the pKb. And if you're familiar with logarithms, just ignore my next 30 seconds or so. I am going to graph what the graph of a logarithm looks like. I find this really helps me learn how this equation's working. So a logarithm kind of looks like this. I should, there we go, that's better. Where this is kind of x, this is the log of x in my graph. And we can see that's the general trend of the logarithmic graph. And you can see a few different key areas for this. The first one is right here. This is when x is equal to 1, which means the log of x is equal to 0. Anything to the left of that, we can see that x is less than 1. X can never be less than 0, but when x is less than 1, the log of x is negative. And when x is greater than 1, the log of x is positive. So over here we have a positive log x value. Down here we have a negative log x value. So we can see, as we relate that to this mole-to-mole ratio, that if this mole of B divided by mole of A, if that ratio is less than 1, we can see we're going to have a negative value here, which means that the pH is going to be less than the pKa. And for that mole-to-mole ratio to be true, we need to have moles of acid than we have moles of base. So that makes sense, that relationship, that the pH is going to go down. This pKa is really talking about when we have an equal amount of acid and its conjugate base, we get this kind of half equivalence pKa value. And maybe I should state that one first, because that's this key part here. If that mole of base divided by the mole of acid is equal to 1, we're at that half equivalence. And we'll talk about that a little bit more when we get into titrations, and you probably have heard about that before. It's just when you have the acid and the conjugate base are of that same concentration, essentially. And when that happens, your logarithm, your pH, is equal to the pKa. Because your logarithmic term in there is just going to be equal to 0. So the final one here is if the mole of B over the mole of A is greater than 1, that means that this value here, we're in kind of this realm, so the pH is going to be greater than the pKa, which means it'll be more basic in that case. So anywhere over here, you're more basic than the pKa. Anywhere over here, you're more acidic than the pKa. That doesn't mean you're necessarily acidic. You could be still basic, but the pKa would just be around like 8 or 9 in those cases, probably. So now let's actually run through and do the numbers for this. They're telling us the moles of phosphoric acid and the moles of the base, and they give us enough water to make this much solution. Like I said, in this buffer solution, we don't really care how much that volume is. So I'm just going to completely ignore that. And we are going to determine what this is. Now, first, we need to look at phosphoric acid. We need to find a Ka value. So Ka of phosphoric acid, well, I went back into Appendix L, or is it I for ionization, and I think that's actually over weak acid. So H is the one I'm looking at. There it is. I highlighted it, phosphoric acid. And we're looking at this top one, this H3PO4. And that's going to have 7.5 times 10 to the negative 3. So that's 7.5 times 10 to the negative 3. We can see the base, the conjugate base for that is KH2PO4. The K is just a counter ion. Oops. Let's switch back to my iPad. There we are. So that K is just a counter ion for that. The H2PO4 is the conjugate base in that regard. And we have our Ka value now. So from that, we can determine the pKa, which is equal to the negative log of that Ka, 7.5 times 10 to the negative 3. That's negative log 7.5 e to the negative 3, which is equal to 2.12. So that's the pKa of what we're dealing with. Now we can plug that in for our pH into the Henderson-Hasselbalch. So that's going to be 2.12 plus log of the moles of base versus the moles of acid. So they're telling us the moles of base, let me get rid of my calculator, is 0.250, and the moles of acid is 0.155. So now I need my calculator back because we're going to do that math. So that's my pKa value. I'm going to grab that, paste it down there. I'm going to add to that the logarithm of 0.25 divided by 0.155. And that's going to equal 2.33. So that's going to be the pH of my buffer. And notice that it's larger than the pKa, and we have more base than we have acid. Since we have more base than we have acid in that buffer system, we're going to be higher than that pKa value because this second log term here is a positive number. And that's what I was saying when here. So just it's a way to double check. If your math ends up saying the opposite or something, you probably did something wrong, and you want to go back and check your science, check your math, and make sure you have the right values in there. It's a good way to check to make sure your answer makes sense. So for 89, this is a fun one. Really, they're asking us for the mass of this ammonium chloride that needs to be added to 0.75 liters of a 0.1 molar solution of ammonia. So ammonia, we looked at or I don't know if we did look it up. I looked it up, and its Kb value, because it's a base, is equal to 1.8 times 10 to the negative 5. And we're going to give it, or to give a buffer solution of pH of 9.26. Okay, and they say assume the volume doesn't change when you add the solid in there. So let's assume the volume doesn't change. So that Henderson-Hasselbalch equation is basically what we're going to be working off of, but we're going to do a little bit of manipulation of it to find all the values we're looking for. So that Henderson-Hasselbalch says pH is equal to pKa plus the log of the mole of base divided by the mole of acid. So we need to use that, but ultimately they want to know what that mass is. But we're going to use that to determine, in this case, this is the acid, NH4. So we are going to determine what the moles of acid are, and then use that to determine the mass of the acid. So to just find all the variables we need in here, we need the pKa. To do that, we need to use the Kb value to find the Ka. So to do that, that's Kw divided by Kb, which is going to be equal to 1.8 times 10 to the negative 5 divided by, I did that wrong. That should be the denominator, where 10 to the negative 4 is, or 14. The heat's getting to me. 10 to the negative 14 divided by 1.8 times 10 to the negative 5 will give you our Ka value. (10 to the power of negative 14 divided by 1.8 e to the negative 5 is equal to 5.56 times 10 to the negative 10. And that's our Ka. To find our pKa, we have to take the negative log of that value. So that means that pKa is equal to 9.255. And I went one more sig fig on this one, because if I rounded it here to 3 sig figs, I'd be at the same value there. And right away, I would say we have an equal number of moles of base to moles to acid. And in reality, it's real close, but it's not quite there. And we want to ultimately find the moles of acid so we can determine the mass of that acid. So now that we have the pKa value, I'm going to write just kind of what I'm going to go about. The moles of that acid is equal to the mass of that NH4Cl, which is ultimately what we want to find, divided by its molar mass. Because anytime you have the mass, which is usually in grams, so we divide it by grams per mole, we're going to get moles, and that's going to be our moles of our acid. We know the moles of base is going to equal, well, they tell us the concentration of ammonia solution, so that's 0.100 molar. I'm going to multiply that by the volume that we have of 0.750 liters. So doing that math, it's really just moving that decimal place over by 1. So that's 7.5 times 10 to the negative 2, or 0.075. So now we have our moles of base. So now I'm going to jump over to our equation and do a little bit of rearranging, because what I want to do is solve that for the moles of acid. So in this case, I can say that the pH minus the pKa is equal to log of the mole of base divided by the mole of acid. I can then take each of those values to the, or 10 to the power of each of those values, and then say that 10 to the power of pH minus pKa is equal to that ratio of mole of base divided by mole of acid. And then I can essentially swap the mole of acid and that 10 to the power of pH minus pKa. Really, I'm multiplying by a fraction on both sides, but I get the mole of acid is equal to the mole of base divided by 10 to the power of pH minus pKa. It's a little hard to read there. Let me rewrite that a little bit bigger. 10 to the power of pH minus pKa. So now I have that moles of acid, and I know the moles of the base here. I know what the pH is. 9.6. I don't think I wrote that here. Let's write it. pH equals 9.26. And we know that pKa is 9.255. So on. We can actually solve for that moles of acid. So I'm going to plug in these values now. That's 7.5 times 10 to the negative 2 for the moles of base, divided by 10 to the power of 9.26 minus that 9.255. So taking 7.5 times 10 to the negative 2 and dividing it by the difference between 9.26 minus this value we got up here gives me 15.58. I did that wrong. Whoop, let's do that again. This should all be the exponent in the of a 10. So let's do that again. 10 to the power of 9.26 minus, oops, that guy. Which brings me to equal 7.42 times 10 to the negative 2. And we can see that's pretty close to the 7.5 times 10 to the negative 2 that we had, but it's a little bit less, right? So like we said, when I calculated this pH to begin with, it's almost 9.26, but it's not quite there. So we're going to have a little bit less moles of our acid than we have of moles of our base. So now that we know how many moles of the acid we have, we can determine, well, what the mass is. So again, if we have the mole of acid, we can multiply that by its molar mass to get the mass of, in this case, NH4Cl. So the molar mass of NH4Cl, ammonium chloride, is really going to be the summation of all the atomic masses. So I'm going to write those out. I'm just going to write out and plug in my moles while I'm at it. 7.42 times 10 to the negative 2 times the molar mass. So nitrogen is 14.007 grams per mole, plus 4 times hydrogen, which is 1.008, plus chloride, which is 35.453. Is that right? Yeah. Okay. And that's all going to be in grams per mole. This is moles, so I can see that that cancels out with my moles. I get grams. I'm getting a mass at that point. So I can take my, yep, there it is. I lost my value. So that's my moles of acid. I can multiply that times 14.007 plus 4 times 1.008, that's hydrogen, plus 35.453, which is chloride. Close my parenthesis. Make sure, yep, that should be good. And that gives us 3.968. I want to round to 2 sig figs or 3 sig figs. So that should be 97 times 10. Oh, no, 97 grams. NH4Cl. Excuse me. So that's the mass of that ammonium chloride that we need to add to get that pH of 9.26 exactly. And that's kind of the process we have to do it. It's kind of a weird system where we have to figure out which one we're missing, solve for that one, and then convert it to the right units, in this case, mass. So I'm going to jump ahead to number 94, which will be the last one I do today, which is a titration problem. I want to make sure I got to this. I didn't erase it. Let's... That was all my work from before. Now to redo all that. So we have a titration. Calculating the pH of the following points in the titration of 40 milliliters of 0.1 molar barbituric acid. Has a Ka value of 9.8 times 10 to the negative 5 with 0.1 molar KOH. And then they have a few different stages that we want to calculate this at. When there's no KOH added, when there's 20 milliliters, 39 milliliters, 40 milliliters, and 41. So if we were to graph a titration curve, let me go down and over. This is going to be my pH. Let me draw that a little lower. So down here, so this is the pH. I'm graphing the pH versus the volume of KOH that I add. We'll see it starts off kind of down here and then curves up and then goes over like that. That's kind of the general shape of a titration curve. And there's a few different key points along this curve that I want to talk about. The first is the initial point here. In this case, it starts out just as a solution of weak acid. So that weak acid has no base added to it, and it comes to an equilibrium at a certain pH. That concentration of hydronium, we can say, is equal to a certain quadratic equation. I'm not going to go through the derivation of that, but it equals this negative Ka plus the square root of Ka squared plus 4 Ka times the concentration of the acid divided by 2. So that's called the quadratic equation for a weak acid. And that's how we can determine that concentration of hydronium before we add anything. And then from there, we can determine the pH. There's this point here, and that first horizontal line here, this section, is basically where we have a buffer. So all throughout there, we have a buffer solution. And that buffer is where we are looking at the relationship between the moles of base versus the moles of acid. And right there in the middle, we have our half equivalence point. And we mentioned that earlier. That half equivalence point is really going to be where the moles of acid is equal to the moles of the conjugate base. And we have this equilibrium where the pH is equal to the pKa. And then shortly after that buffer, we see that the moles of base start to increase dramatically compared to the moles of acid. The pH shoots up until we hit this point right here. It's nearly vertical at that point. It's exactly vertical, actually. We call that the equivalence point. EP, EQ. And that's when the moles of the conjugate base have taken over, and you basically have no moles of your original acid. You just have those moles of conjugate base there. And for here, we use a similar quadratic formula, but this one we're calculating the OH minus. And that's going to equal negative Kb plus the square root of Kb squared plus 4Kb times the concentration of my conjugate base, all divided by 2. I'll lower this down just a little bit. I should mention anywhere in this buffer, it's the Henderson-Hasselbalch we want to use. There's a few exceptions to that, but we're not going to get into it in this class. So after the equivalence point, once we add even a little bit more volume, so anything really beyond this point here, we treat as a strong base. Because after that, it's really the strong base is taking over, and the weak acid doesn't really have any effect on the pH. It's just that strong base that's going to affect it. So that strong base is literally just going to be the pH of, well, we can calculate the pOH, which is equal to a negative log of the concentration of OH minus. And then in turn, calculate the pH from there. So we're going to run through and do that for these quick things, and then we'll be done for today. The initial one is when no KH is added, so we're going to be using this quadratic for the weak acid. And that's going to be negative 9.8 times 10 to the negative 5 plus the square root of 9.8 times 10 to the negative 5 squared minus 4, what would we say, plus 4 even, plus 4 times 9.8 times 10 to the negative 5 times the concentration of the acid, which was 0.100 molar. We're going to divide that whole thing by 2. I know it's a lot to really look at, but it's really just following this equation and plugging in our Ka values, which they give us, and that concentration of the acid. So that's going to be, I'll clear this, negative 9.8 times 10 to the negative 5 plus the square root of 9.8 times 10 to the negative 5, and put a square there, plus 4 times 9.8 times 10 to the negative 5 times 0.1. And we're going to divide all of that by 2. Let's make sure I get all of it, because I think I forgot a parenthesis at the beginning, which I always forget the parenthesis at the beginning. There we are. So I got that whole numerator in parentheses, and then I'm dividing it by 2 to give me a concentration of hydronium equal to 3.08 times 10 to the negative 3. So I can take the negative log of that value to find the pH. I'll just put an arrow. The pH is equal to 2.51. 2.5, 2 sig figs. So before we even add any base to it, we have a pH of 2.5. For part B, now we've added 20 milliliters of KOH to the solution. So initially, I'm going to write it up here, the initial moles of acid. So that's how much acid we started out with before we added anything at all, is going to be equal to that 0.040 liters times the concentration of, that was a weird 0.100 molar. Put units in, which is really equal to I'm going to multiply those together, 0.0040. And that's going to be moles. So really 4.0 times 10 to the negative 3 is what we got there. So that's my initial mole count, and we're going to use that for the next few, because we need, every time we add a little bit of OH to it, we're going to reduce the initial moles of acid or the moles of acid by that same amount of moles of base that we add, and we're going to increase the moles of the conjugate base by the same amount as well, because every mole of OH we add steals a hydroxide or a hydrogen ion from our weak acid and creates a conjugate base. So for part B, we take that initial mole, we have that there, and we want to find also now the mole of the base that's been added and created. This is the mole of the conjugate base, which is equal to the volume of OH minus added liters times the concentration of the OH. So in this case, it's 0.100, same concentration as the acid. So here we're going to end up with 0.002 molar, or moles. So we can determine the difference there. If that's how many moles we have, really, I guess we don't want the difference. We want to determine how many moles of acid are left at this point. So that's going to equal 0.0040 minus 0.0020, which is equal to 0.0020. Because we ended up converting half of the moles of acid into its conjugate base at this point, because we have the same number of moles of acid as base. And we can plug that into the Henderson-Hasselbalch to find the pH, which is equal to the pKa minus or plus the log of, well, it'll be 0.002 divided by 0.002, so that's just going to be 1, and then the log of 1 is equal to 0. So the pH is just going to equal the pKa at that point, which we can plug in and find out the negative log of 9.8 times 10 to the negative 5. So the negative log of 9.8 e to the negative 5 is equal to 4. So at that half equivalence point, we have a pH of 4.0. So we can see the progression. We're adding OH minus to it, we're adding that hydroxide, and we're increasing the pH value as we go along. But it only increased by a little bit, went up 1.5 levels on the pH scale by adding half of the same volume, by getting rid of half of those moles. So if we look at part C at 39 milliliters, so at 39 milliliters, we have basically the same thing going on. We still have that buffer. It's almost not a buffer anymore, but we can see that the moles of base are going to equal 0.039 liters of 0.100 molar, which is equal to, I don't need that, well, it's going to be 0.0039 mole. And we started out with 0.0040 mole. So that means the moles of acid, which are left, is equal to 0.0040 minus 0.0039, which is equal to 0.0001 mole. So that's the moles of acid and moles of base we have at this point. And we know the pKa from up here. So plugging into the Henderson-Hasselbalch, we can see that the pH is going to equal 4.0 plus the log of 0.0039 divided by 0.0001. So that's going to be 4, or I'm not going to say 4. I'm going to actually go up and grab, it was a little over 4, plus the logarithm of 0.0039 divided by 0.0001, which is equal to 5.59 or 5.60, we'll say. So we can see almost at equivalence point now. We've added 39 of the 40 milliliters we had. We have barely any acid left in there. We're still at a pH of 5.6, which is still pretty acidic, really. And at that point, we're like right here on my scale. You can see that, kind of right in this point here, just before it's really going to take off. And we'll see what happens in part D when we have 40 milliliters. So we have equivalence in volume, and since they're the same concentration, they're both 0.1 molar here and 0.1 molar there, we're going to end up with the same mole to mole ratio. So once we have that same mole to mole ratio, we can see that here in part D, so where the mole of B is going to equal, actually I'm going to flip to the next page. No, I'll leave it. I have enough room on here. I'm going to have a part E as well, so I was going to just use the next page for it. But we can see the mole of B is equal to 0.04, because we have 40 milliliters now, times that 0.100 mole per liter. So that is just going to equal that 0.004 moles, and the mole of A minus the mole of B is equal, that's the initial moles of A, is going to be equal to 0, because we have the same amount of moles of both of those, so which means there's no acid left, at least no significant volumes of acid left. So at this point, to calculate the pH, we need to use this quadratic equation, because now essentially we just have a solution of a weak base. All of the acid has turned into its conjugate base at the equivalence point here. Excuse me. And we are just trying to determine what that concentration of OH minus is. So the concentration of OH minus is going to be equal then to this quadratic formula we had up here. Negative Kb plus the square root of Kb squared plus 4 Kb times the concentration of that base, all divided by 2. Now in this case, we need to find out what that Kb is. Kb is equal to the Kw divided by Ka. And we know what Ka is because they gave it to us. 9.8 times 10 to the negative 5. So that's just going to be 10 to the negative 14 divided by 9.8 times 10 to the negative 5 is equal to Kb. 10 to the power of negative 14 divided by 9.8 e to the negative 5 is going to give us a Kb value equal to 1.02 times 10 to the negative 10. So now plugging into that quadratic formula, oops, I was trying to get rid of that. This is negative Kb, which is going to be 1.02 times 10 to the negative 10 plus the square root of, I'm going to move all this up here so I have a little bit of extra space, because I'm to be 1.02 times 10 to the negative 10 squared, Kb squared, plus 4 times A times 1.02 times 10 to the negative 10 times the concentration of our conjugate base. Now that's where we run into a little bit of trouble, because that concentration of base, we know how many moles are there, but we need to make sure we know the total volume of our solution at this point, because it's really, we started out with that 40 milliliters, but since then we've added 40 milliliters. So really we have 80 milliliters at this point. So we can put that moles in there of 0.004 mole divided by 0.004 0.080 liters. And that's going to be our concentration. Divide that whole thing by 2. So we can see just by plugging in the values of what we need in there, we can get this concentration. And then the rest of it is calculator work. So let's not forget my parenthesis, negative. Luckily, I got my concentration, my Kb value, saved up here, so I can plug that in. Plus the square root of, grab again my Kb value. First, I'm actually going to put a parenthesis in, then grab my Kb, so I can close that and square it. So this should be Kb squared. And I'm going to add to that 4 times that Kb value times the concentration. That concentration, I said, parenthesis, 0.004 0 divided by 0.08. Close my parenthesis and close another parenthesis for my numerator. Divide it all by 2. I get a syntax error because I left something out. What did I leave out? This did not need a parenthesis. That initial parenthesis was for my whole numerator. There we go. This is all going to be equal to an OH minus concentration of 2.26 times 10 to the negative 6. So we can determine our POH, which is equal to negative log of 2.26 times 10 to the negative 6. Negative log of that value, which is equal to 5.65, we'll say. And then we have to find the pH. So the pH is equal to 14 minus this 5.65, which is equal to 8.35. So there is our pH at the equivalence point after we've added an equal amount of moles of acid to the moles of base. And we can see that it's steadily rising up from the last time. It went up dramatically by just adding 1 more milliliter of base to it. And that's where it's shooting up in this direction here. And it's getting to that, it's really increasing in rate and determining, or it's increasing in rate based off of the volume we added. And anything after that, we basically just treat as a strong base. We just look at how many moles of base were added after the equivalence point divided by the volume that we have. So for part E, which is pretty quick and easy, we have 41 milliliters. Again, I left all my notes. Luckily, that was part D and E. So part E is really just saying the mole of strong base added after the equivalence point. After that EQ is what I've been calling it. Equivalence. So really, in this case, at equivalence, we had 40 milliliters. So we want to take whatever volume we're looking at. In this case, for part E, we're looking at 41 milliliters. I'll write that as liters minus 0.040 liters. So this was our initial volume at equivalence point. This is the volume we're looking at now after adding and titrating in that much KOH. This is going to equal 0.001 liters. So if we were to multiply that by 0.001 times 0.100, because that's liters times molarity, this is going to equal then our moles, 0.0001 mole. And that's how much mole of strong base we've added to the solution after the equilibrium. The volume, the total volume, is equal to 0.041 liters. That's how much KOH we've added, plus the 0.040 liters of the initial acid solution, which is equal to 0.081 liters. We have moles, we have liters. We can find out what the moles per liter is, which is our concentration of the strong base. So that's 0.0001 mole divided by 0.081 liters is equal to 1.2345679. Look at that. 1.23 times 10 to the negative 3. Now that we have that, remember this is the concentration of OH, the hydroxide. So we can say that POH is equal to negative log of 1.23 times 10 to the negative 3. That's negative log of this guy, which is equal to 2.9. So the pH is going to be equal to 14 minus 2.9, which is, oops, rounding errors are bad. Grab that value. That's going to be 11.1. And that is the pH after adding just 41 milliliters. So you see how much it shot up from 39 milliliters at 5.6 to reaching equilibrium and going up to 8.35. And then 1 milliliter past that, it's at 11.7, or sorry, 11.1. And that's this part right here. It shot up to this part here, just a little bit above. But now we have a much higher pH than we had 2 milliliters previous. And that is the end of our titration problem. That's all I have for you today. Thanks for watching this whole thing. I went way over my time, but that's been fun. I really enjoy talking about acid-base chemistry and stuff like this. So be sure to tune in on Saturday at 2 p.m. as well. I also have drop-in hours after that up until 5 p.m. And you can always make an appointment with our tutoring, our chemistry tutor, Amir, on the Pingy app. So if you haven't tried the Pingy app, download that and just log in with your PSU credentials, and you should be able to get tutoring help for chemistry or any of the other subjects we offer tutoring for. And you can also drop into my drop-in hours on Saturday. Thank you for everything, and enjoy yourself, and have a great day.